From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. Let's see, what happens a week from today? What? No class? Well, no lecture. Okay. So we have a little exam a week from today that covers chapters 1 through 7. And who do we play in basketball? Ask you that. No, I don't think it's, I think it's California. I think Stanford's on Saturday. So about the time I'm grading the exams is when we play Stanford. So you better hope. Okay. Last class, right at the end of the class, we were talking about, well, we had gone through the free spectral range, and we saw the problem we had with a Fabry-Perot on measuring small differences in wavelength if we had a wide spread of wavelengths present, the free spectral range problem. So right at the end of class, we had gone to this section 7.3.3, spectrometry with a Fabry-Perot etalon. And what we said here was that we have a source here that's a slit source. And so we'll put a lens here to collimate that. And so we collimate, so in this dimension we just have a collimated beam, don't have a lot of angles present. While in and out of the paper here, we will have a lot of angles present incident upon this prism. Forget about the Fabry-Perot for a second. Incident on the prism. After the prism we place a lens, and in the focal plane of the lens we will have an image of the slit. And if we have more than one wavelength present, we're going to have a lot of images of this slit here for the different wavelengths. Now, inside this, after this collimator here, we place a Fabry-Perot. And we think we have a Fabry-Perot where we have very high reflectivity. And so only certain, for a given angle, only certain wavelengths are going to be transmitted here. So if we come over here and see what do we have here? Well, if we had only, if we had only the Fabry-Perot, what we would see would be some circular ring thing here. Because of the prism, the different colors go in the different directions. We have a slit here, so we don't have, well, I should go back here. With the Fabry-Perot, if we had angles at all different directions, we'd have circular fringes. But since we have angles incident in one direction is collimate, in the other direction we have a lot of angles present, all we would have would be these little arcs from this circular ring pattern, because we don't have angles present to give the rest of the circle here. Because of the prism now, the different colors are going to be dispersed here, and so here we will have rings, a portion of rings, arcs for red light. Here we'd have arcs for the green light. Here we'd have arcs for the blue light. So does everyone see what we're looking at here? I know some of the previous classes often had a little trouble right at this point, but no one here, I guess, does. Good, okay. The prism here, as we say, does a gross separation to eliminate or at least reduce the problem we had with the free spectral range. Prism doesn't give us a super high resolution, but the Fabry-Perot will give us a high resolution. So this is kind of a neat trick. And you see this many times in optics, that whatever you're trying to do, you combine two things. One will do the coarse measurement, and something else will do the fine measurement, and you put them together, and you get a large dynamic range. In this case, we can have a wide spread of wavelengths, and we still can have high resolution, high spectral resolution. Any questions? Ready to go on? Okay. Well, that was 7.3.3. 7.3.4 here. We're going to talk about a scanning Fabry-Perot. So we're going to have a Fabry-Perot cavity here. I show plane mirrors. They may not always be plane mirrors, but that's the only thing we've talked about so far till the next section. And I'm going to have high reflectivities here. And if I have a collimated beam incident on here, whether I get any light through or not depends upon the spacing of the Fabry-Perot and depends upon the wavelength. And so what we're going to do here is that we will set this up where we focus all the light on a detector, and then we'll just look at the output of the detector on the oscilloscope here as we change the separation between the two plates in the Fabry-Perot. And so if we have a few wavelengths present here, like from a laser source, we have a few modes, every now and then the separation will be just right, such that we'll get light through. And we'll see a little spike here on the oscilloscope. Change the separation a little bit more, the light doesn't get through until we get to another separation where another mode will get through. And so for maximum transmission here, 2D is m lambda, normal incidence. I have neglected any phase changes on reflection, and phase changes on reflection will not change the performance of this. All it will do is it will change the separation such that we get light through. But if I'm just going to sweep this through and watch the spikes on the oscilloscope, the absolute distance here to get the spike will not affect the results. And so we can just say, well, how would we have to change D in order to change the wavelength gets through by some delta lambda for same order? So just 2 delta D is m delta lambda. And so that's 2D over lambda times delta lambda. And thus we have the result here that delta D over D is delta lambda over lambda. So if we keep track of how we sweep this across, not what the absolute D is, but how D changes, then we can determine how the wavelength changes for the different peaks here. So I would guess that a few of you have used this in lab to look at laser modes, and it works pretty well, right? Pretty handy little device. Any questions? Okay. So scanning Fabry-Perot. That was 7.3.4. Now we're going to have to go back to paper and pen here for a while. Paper and pencil. And we'll go to 7.3.5. And this is on a spherical Fabry-Perot. So far we've only talked about Fabry-Perots where the plates are plane. But you can probably go to spherical ones as well. And the reference where I've taken this material from, it's in a lot of places, but one reference is from Sohn's book on optical interferometry, about page 119 it's described. So we're going to put two spherical mirrors here. It's supposed to be spherical mirrors. And they're going to be separated at a distance d. And we're going to make it such that the center of curvature of this mirror falls, well, let's draw an axis first here. The center of curvature of this mirror falls on the mirror over here. And the center of curvature of this mirror falls on the mirror over there. So both these mirrors have the same center of curvature. And maybe I'll write here that center, both of them have the same radius of curvatures. And the center of curvature of each mirror is located on the opposite mirror. Okay. And let's see, how is the focal length of a spherical mirror related to the radius of curvature? So what, it's 1/2 the radius of curvature. And so the two focal planes here are coincident right in the middle. Okay, write that down. Two focal planes coincident in the middle. So, okay, then the next thing we normally do, or often do on this, is that we're going to take these two spherical mirrors and I'm going to put a very high reflectivity on half of the mirror, half of each mirror. Let's say the lower half here. So lower half nearly totally reflecting. Upper half is semi-transparent. Okay. And I guess the other thing, I'll get a different color here. This point here I'm just going to call M1, and this point over there I'll call M2 for the mirror 1 and mirror 2. Let's see, what else? Well, let's trace a ray through the system, I guess is the next thing to do. Let's take a ray here, and so it goes like so here. And I guess I call this point I here. And I call this point J. And of course what gets through is T. So this is the center curvature of this mirror is over here. And so the ray comes in here. It's going to be imaged down, someplace down here. Right? Such that this distance is equal to that distance. Okay. Now, likewise, the center curvature of this is over here, and so on. So this guy is going to come down here, who knows where, down here someplace. And I call that J. I'll call that J prime, and I'll call that I prime. And then this guy is going to image him back up here. Oops, same place there. Okay. So the light goes here, 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 and back there. And lo and behold, we're back where we started from. Okay. And I guess you might have some light that comes out here. We call that T prime. And then this is going to go through here again. Okay. And just keep repeating itself. Okay. And so the total path that this light travels, and this is, we're going to be neglecting any off-axis aberrations. We're going to assume we have small mirrors. So I'll write that down here. Neglecting aberrations. Well, we will make some comments about them in a minute. But neglecting aberrations, the distance that this travels, and going one complete cycle is what? Just 4D. And so if I look at the phase, neglecting any phase changes on reflection here, but looking at the phase difference between the consecutive beams that come out here, we would have that the phase is what? 2 pi over lambda times 4D. Okay. And the first thing, well, one of the first things we notice is, we get a 4D here instead of a 2D. That's kind of interesting. Where's my cosine theta? Yeah. So this is forgetting about aberrations. This is independent of theta. Okay. So we send this beam in here, and we're going to get a beam out. It's not going to have circular fringes anymore, but we're going to get a beam out where we have some, let's just say some tint across the whole beam. Okay. And so this is actually pretty easy to align. You just line it any way you want here. Again, neglecting aberrations. Line it any way you want, and you're going to get a beam out here with uniform illumination across the beam, or whether it's a bright fringe or a dark fringe or whatever, of course, depends upon D and depends upon the wavelength. But it doesn't depend upon the angle. So you just have a flat tint over the whole field. And it ends up, you use this type of cavity often in the scanning Fabry-Perot. When we scan here, we don't scan very much, so we don't spoil the fact that this the center curvature, each mirror falls in the opposite mirror. We don't spoil that by very much. And it's very easy to align. And it's 4D instead of 2D and no theta. Okay? Well, in real life, we have aberrations. Okay? I don't know if you've noticed that yet, but you do. Okay. So what happens if we have aberrations? Well, what's going to happen here is that you're going to get, over a small field angle in a small region here, you will get the flat tint that I've talked about. But you're going to find that you're going to get some circular fringes around that due to the aberrations in the system. And what you generally do is you make the apertures here fairly small, and that will reduce the aberrations that you have. This works pretty well. Any questions on it? So
I'm just meaning
a flat tint, I mean well, it's uniform and a uniform color. And the color depends, we have this expression here for the phase difference. And so some wavelengths will get through and some will not get through. So you end up with some resulting color, which I'll call a tint. Okay. Any other questions? Okay. You're all experts on spherical Fabry-Perots. Is that true? Good. And at least by next Thursday you will be. Okay, 7.4. Well, rumor has it around optical sciences that I really love the fecal interferometer. I'm sure if that rumor is not around, there's something's wrong. Okay. So fecal. First off, what does fecal stand for? It stands for fringes of equal chromatic order. Okay. And, before, we've talked quite a bit about multiple beam fringes. And a lot of it's working with monochromatic radiation. Now what we want to do is we're going to use white light. And we're going to combine the multiple beam interferometer with a spectrometer. To measure thickness variations. And the nice thing here is, one nice thing is that you're never going to have an ambiguity whether it's a high spot or a low spot, as we'll see. You're going to have super resolution down in the angstrom type range. It's a very neat, it's a neat little instrument. And it's not very well known. In fact, you can maybe impress your friends with the fact you know what a fecal is. I don't know. But anyway, it's not very well known. But, of course, where can you find out more about it? The Bible. Born and Wolf has a very good section on the fecal. And I think we have a fecal in optical sciences, although I haven't seen it in a long time. But I plan to try to find it, because if I can find it next semester when I teach the optical testing lab, I'm going to have the fecal as one experiment, because I think it's really, really cool. Okay, well, there was a handout, and again, I apologize for those of you out in TV land, at least those of you watching us live. You don't have the handout. It's in the mail, I guess. But it's not too hard. You'll be able to sketch it here. And those of you who didn't, is there anyone here who does not have the handout? You might walk over to the side and pick it up. Okay, we're going to start out here with a white light source. And it could be a point source, or it could be a slit. But in any case, we're going to illuminate the sample with a collimated beam of light. And the sample, next to the sample, we're going to put a reference surface. And these two surfaces here are going to be coated to very high reflectivity. And then maybe that's one disadvantage here. We're trying to measure the flatness of this sample, and we do have to coat it to a high reflectivity because we need high finesse fringes. Okay? So, sample, reference, close together. We will image this onto a slit. And so what that really says is that I'm not looking at the whole sample. I'm looking at only a slit portion of the sample. And maybe that's a drawback too, in that I'm only seeing a slit portion of the sample at any given time. And that becomes the entrance slit to a spectrometer here. So we'll put in a lens here, put that slit at infinity. Light will go through the, well, I draw a prism, I guess it could be a grating, but something to disperse the light. A lens here will image the slit down here. And so we're going to get different wavelengths imaged in different locations. And if I had only a single wavelength present, then I would just have a nice image of a slit here. Now let's think for a second before we begin writing down some equations. Is that this is I said high reflectivity here, high finesse. And so some wavelengths are going to be transmitted and some wavelengths are not going to be transmitted. So I will get an image of a slit over here for the wavelengths that are transmitted, and I will not get an image, for wavelengths that are not transmitted. And whether a wavelength is transmitted or not depends upon the separation between the plates. And so if this sample here is not flat, certain portions of the sample will transmit one wavelength and other portions will transmit a different wavelength because D, the separation between these two, will vary. And so by looking over here at what wavelengths are present, I might be able to determine what D is and hence determine height variations on the sample. So before we go through any equations, do you kind of see physically what's happening here? Okay, so I'll celebrate that by taking some coffee. Okay, well, maybe we better write down some equations. I'll move this off to the side, but remember what it looks like as we go through here. So we have, transmitted multiple beam fringes. Transmitted light. And so we have I is some I max divided by 1 plus f sine squared of delta over 2. And what is most important here is that delta is 2 pi over the wavelength 2 n d cosine theta plus some phase change on reflection. And for simplicity, I've written same phase change from both surfaces, but I don't think that is a requirement. And we'll get a bright fringe when this is equal to 2 pi times an integer. Okay? Then the sine squared will be equal to 0, and we get I max. So we have this equation here, and let me just divide through by 2 pi. So we have m is equal to phi over pi plus, and I'm going to let, let's say we're at normal incidence, so cosine theta is 1, and let's say we just have air in this gap, so n is very close to 1. So I set that equal to 1. And so this becomes phi over pi plus 2d over lambda. Okay. So this is what we have for a given fringe of order m. And so the kind of interesting thing here is that d for a given fringe d over lambda is equal to a constant. Okay? That's kind of interesting. And I can solve here that whatever wavelength gets through here for the mth order, I'll just call that lambda sub m, is equal to just 2d divided by m minus phi over pi. Okay. So our goal here is to determine the thickness d, because if we assume one of these two surfaces we're looking at is perfectly flat, when I know d, I will know the height variations in the other sample. So what we do here, we're going to, I'll just solve this for d, okay? D is what, m minus phi over pi times lambda for that order, m over 2. Now, it's going to be a little bit complicated, or can be, if phi is a function of the wavelength. And what I want to do here is to assume that that's not the case. I'm going to assume that over the wavelengths of interest, phi is approximately a constant. And this is true for a lot of cases, like silver, for example. Most cases, this is true. But if that bothers anyone, I'm going to give you a reference. And, well, one reference on this is Born and Wolf, where they could say more, what if phi is not a constant. And another one, because I want to mention her name, is Jean Bennett. It's an old article in JOSA, volume 54, page 612, 1964, where she goes through and shows how to handle this if phi does vary with wavelength. And I wanted to mention this because there are some You know, some authors out there, you want to read everything they publish, and Jean Bennett is one of them. She has done some very, very excellent work during her career. Okay, so back here, our goal is to solve for D, and we're going to assume that over the wavelengths that we look at, phi is a constant here. And so if I think, what do we see in this region here for the fringes? And let's say we have a surface that is basically flat, but it has a little channel cut in it. And what we'll see then will be the following. So first off, we see that we have wavelengths along the x-axis here. So I'll draw that. Wavelengths along the x-axis. And if the surfaces were perfectly flat, well, let's do that first. I would just see images of the slit. And, you know, this is order m. This is order m plus 1. This is order m plus 2, and so on. Everyone agree with that? That would just be, if D is a constant, I'm going to get these certain wavelengths transmitted through, and I would just get many images of the slit. But of course, that's not very interesting for us when the surface is perfectly flat. You always want to test surfaces that are not perfectly flat. Funny, you want to make surfaces that are perfectly flat, but if you're in a testing business, you don't want to test them. So if we have, you know, maybe we have a surface or a fringe that comes out looking like this. I'll just show two orders here. And order m and order m plus 1. And let's pick a couple of surfaces, a couple of points on this surface. Let's pick a point here. Call that point 1. And then, so that's, you know, this is an image of our slit. So this is sort of an image of that slit portion of the surface. That's point 1 on that surface in fringe order m plus 1. Here's point 1 in fringe order m. And likewise, we can pick some other point here, 2, and the corresponding image is over here, 2. Okay. So does everyone understand what I'm doing with this drawing here? Because that's the whole key. Once you understand this, the rest is going to be trivial. Either you understand or you don't have the nerve to say you don't. So. Okay, good. So I want to find the difference in the separation D for point 1 and point 2. That will give me the height difference on my sample between point 1 and point 2. And so I say delta D, which is D2 minus D1, is equal to, well, I have this equation right there. So that's equal to, well, I can say that's m minus phi over pi and I have lambda for point 2 of order m minus lambda for point 1 order m. Okay, so I want to find the difference in D for point 1 and point 2. I'll look at this fringe. That's of order m. I want to find the difference in 1 and 2. And so that's wavelength for point 2, order m. That's wavelength for point 1, order m. Okay? So if I knew this wavelength and this wavelength, and I can read that off some dial in my fecal, and if I knew this quantity right here, then I could calculate the height difference between D and between point 2 and point 1. So this I can read off some dial in the instrument. This I don't know. So some way I have to eliminate this quantity. So we must eliminate m minus phi over pi. And so the way I do that is that we're going to look at, say, 0.1 on 2 consecutive fringes here. So we know that d is the same. I mean, 0.1 has some d. So the same d there as there. And so we can write here that m minus phi over pi for lambda 1 m is equal to m plus 1 minus phi over pi lambda 1 m plus 1. So I simply look at 0.1 for 2 consecutive fringes. I know that d is the same, and so I know that this quantity for order m must be equal to this quantity for order m plus 1. Okay? And so I can then just solve this for m minus phi over pi. And that's equal to then lambda for 0.1, fringe m plus 1, lambda for 0.1, fringe m, minus lambda for 0.1, fringe m plus 1. So I read these wavelengths off my spectrometer dial, the dial in the spectrometer, and I can then calculate m minus phi over pi. I can then take this and plug it back into my expression up here, and we will get the answer that delta D is lambda 1 m plus 1 divided by lambda 1 m minus lambda 1 m plus 1. And up here we have lambda 2 m minus lambda 1 m divided by 2. Okay. I'll draw a nice big red box around this. And so by measuring lambda 2m, lambda 1m, lambda 1m plus 1, I can calculate d, or the change in d between 0.1 and 0.2. And we note here that delta d is really proportional to lambda 2m minus lambda 1m. And so this little thing that we get right here, these lines, really are giving us profiles of that cross-section of the sample. Okay. Nope. In space, they look just like this. In fact, I'll show you a picture. Picture from Born and Wolf, okay, of some fringes. And the thing is, we know for a given guy here, this is, okay, this was, you know, we have a slit portion of the sample. This is a fringe of some order. And, 2d is equal to m lambda. So if d varies, m is constant, some order, then lambda has to vary. So this is, the wavelength in hundreds of angstroms, he says here. And so that's what the image of that slit would look like. So it's giving you a profile of the sample. So a small change in d gives you a small change in the wavelength for that fringe. And 2d is equal to m lambda. So if lambda increases, d increases. If d increases, that must be, a low spot on the surface. So there's never any ambiguity about whether a point is a high point or a low point. Falls right out. See it? And you can measure here in the angstrom type range using this technique. Yes, question?
Somewhat general question. Since we're since we're taking our test surface and referencing it against an optical flat, how do you know that the flat is truly flat?
Okay, the question is that in this instrument, like all interferometers, you have a reference surface. And we're measuring the difference between these two surfaces. And the question is, how do we know that the reference surface is really flat? And that is a tricky question. In these instruments, you always have a reference surface. And so some way you have to certify that reference surface. And so you probably want to compare that with several other surfaces. And again, I'll put in an ad for 513 next semester. We do talk a little bit about absolute measurements of surfaces. But that's a tricky thing. How do you know how good your reference is? But probably comparing several surfaces. Bootstrapping your way up is an approach. So that's true. We're only measuring the difference between the two surfaces. Any other questions on this? Okay. Well, the fecal, as I said, it will go down the angstrom range. It's pretty powerful. Maybe a couple of drawbacks to it is that it's you have to coat the surfaces. And if you're measuring down in the angstrom range and you put a coating on the surface, does that coating follow the surface to the angstrom range? The second thing is that you are looking at a given time, you're only looking at a slit portion of the sample. And so if I want to measure a larger area of the sample, you have to look at a lot of slits. And there are, in its day, the fecal was the best way of looking at super smooth surfaces. There are better ways now of doing it. In fact, I spent the last 15 years of my life working on some of these better ways. And chapter after next, I think we'll talk about phase shifting interferometry, which will lead us to techniques that are maybe more powerful today than the fecal. But over the years, it has been a very interesting instrument, very powerful instrument, and I always find it very intriguing how well it works. Yeah, the wavelength scale is determined by your spectrometer, and so it's determined by your prism, your lens, and so on. So if you were to make an instrument like this, you'd have to calibrate it some way with putting in wavelengths of known, or using sources of known wavelength. If you buy an instrument like this, hopefully they have calibrated it for you. Question?
You did in the vertical direction.
Well, in the vertical, the question is what resolution do we get in the vertical direction, and that's a good question here. It's basically a microscope system, and you can get down into the micron type range in the vertical direction. There's always a trade-off between the field that you have and the spatial resolution.
Atomic scale.
You can't do atomic scale. I've been dreaming about that for years, and by coincidence, I actually have a meeting at WICO this afternoon on that very on that very topic of improving the spatial resolution of microscope systems. But I'll tell you, I've been thinking about it for 20 years, and I don't know how to do it, so I don't know.
The question, if one surface is highly reflective and the other isn't, you just get lower visibility fringes?
Yeah, bad news. The question, if one surface is high reflectivity and the other one is not, you get these sharp fringes only when both surfaces have a high reflectivity. And if they don't both have high reflectivity, you get low finesse, and you don't get sharp fringes, and your measurement accuracy is gone. So you have to have high reflectivity. Any other questions? Yes?
With your white light sources, then also, it looks like if you're producing a collimated beam here, is it similar to the ones before, where in one plane you've got collimated and the other plane you've got the angles? Is that?
Yeah, the question on the source here, I guess my drawing makes it look like a point source, and that's great. Point sources are great, except they often don't have a lot of light on them. And so you probably would have a slit here that would be parallel to the slit here. Okay, let's see. Yes?
I have another question. What aberrations in your system, could you comment on what that does to the fringes as far as the lenses? Yeah.
Well, aberrations in the system, yeah, well, you don't want aberrations. I mean, that's bad news. And it will hurt your spatial resolution in Y, and it's going to hurt your resolution in X here, which means that that's going to limit your height resolution. And so no aberrations, please. Okay. Any other questions? Okay, well, that finishes up Chapter 7 on multiple beam interference. Kind of interesting area, I think. So that will take us to Chapter 8, which is multi-layer films, which just happens to also be multiple beam interference. So maybe we're not quite done with multiple beam interference. And I have some notes, which hopefully you picked up. And again, I apologize for people out in TV land that if you're watching this live, you don't have the notes yet. I'll give you a couple of references on this, a couple of very good references on this. So this will be 8 multi-layer films. And for the material that we're covering in this course, Heck's book, a lot of this I just take straight from Heck's book, and some I take straight from Born and Wolf. And I think, to be truthful, Heck took his stuff straight from Born and Wolf. So you might just go back to the source if that's what you want to do. So what we're going to do is we have an optical surface, and this optical surface has some reflection. And we want to some way change what that reflection is. And so we put thin film coatings on this surface to change the reflection transmission for the surface. Sometimes we want zero reflection or very low reflection. Sometimes we want very high reflection. And the procedure, at least the theory for doing this, is fairly straightforward, as we'll see here. It's a little messy, and so we try to do it in some orderly fashion. And we'll end up with what we call the characteristic matrix. And then from the characteristic matrix, we'll solve for the coefficients of reflection and transmission. And then we're going to look at some examples of anti-reflection coatings and high reflectance coatings. And this is an area, for years I told people that if they wanted to make a lot of money, they should go into thin films. Because it's always, any of you working in thin films or planning to work in thin films? No, okay. People don't like money, I guess. But anyway, I told people for years that you get all kinds of jobs out there and you make lots of money. And then about 4 years ago, I got a nasty letter from someone, a graduate from here, who told me he had gone into thin films and he'd just been laid off. And so he thought the advice I'd given him was not very good. So I don't know. You never know what will happen in the future. But thin films are certainly very useful, and I think that you could find a lot worse things to go into. There's also a course here that's taught, has been taught for a number of years by Angus MacLeod. Of course, Angus has retired, but I think that due to popular demand, he will come back here anytime and teach his course, and it's an absolutely superb course. Okay, so we'll start out here with this drawing, and I have to say in my handout, the drawing is not very sharp. So this is section 8.1 on theory. The drawing is not very sharp, and I apologize for that, but you can get the original drawing from Heck's book, and that will be much sharper. So the idea here is that the tangential components of E and H are continuous at an interface. And so we're going to make use of that. And so for my drawing here, I have one layer of thin film, thickness D, index N1. Outside here we have index N0, probably air. Down here we N sub S, substrate, maybe glass or whatever, but anyway, N sub S. Light coming in here, E sub I1, because this is boundary 1, so E sub I incident on boundary 1, K sub I1, H sub I1, theta sub I1. And again, probably in your handout you have a little trouble reading that, but it's all in hex book. Reflected back here, E sub R1, H sub R1, K sub R1. Okay, makes sense. What goes through here? E sub T1, or I, standing for surface 1. Theta sub I2, because that will be the angle incident on boundary 2 down here. Okay. E sub I2, incident electric field on boundary 2, E sub R2. Coming back here, we have E prime sub R2. Okay. So E sub R2 here, and when it gets up to the surface, it's E prime sub R2. Transmitted through here, E sub T2, H sub T2, K sub T2. Now, the other thing I should say is that when I say like E sub R1, that's going to be all the electric fields going in this direction. E prime sub R2 is all the electric fields going in this direction. Okay? And E sub T2 is all the electric fields coming through here. Okay. So, making use of the tangential components of E and H being continuous, we will simply write down here, and I can't show this on the screen all the time because I need a screen for these equations, but we'll keep referring back to this drawing. I'll take a sip of coffee. Maybe 2 sips. Okay. Boundary 1. E sub 1. And so that's E sub I1 plus E sub R1. That's what's outside. Inside, it's E sub T1, E prime R2. So outside we had E sub I1 and E sub R1, and inside we have E sub T1 and E prime R2. And then we go back to E and M. We know that H is square root of epsilon naught over mu naught n K cross E, non-magnetic surfaces here, materials. We know that N is defined as C over V. And so that's the square root of mu epsilon over mu naught epsilon naught. And so this was our equation for the continuity of E at boundary 1. Continuity down here for H. And again, I picked this so the case we're looking at, E is perpendicular to the paper and H is in the plane of the paper. So when we do H, we get some cosines here. And we have to keep track of the direction of the E's, so we get some minus signs. So we get H sub I is square root of epsilon naught over mu naught, E sub I1 minus E sub R1, N naught cosine theta I1. And that's equal to square root of epsilon naught over mu naught, E sub T1 minus E prime R2, N1 cosine theta I2. So I'll say that I typed this in Mathematica because I love their equation editor, but I would not, this is what I would call a display equation. It's not an equation to calculate from, because mathematics would see that prime and boop, it'd take a derivative right away, and that's not what we want to do here. So this is a display equation. Okay. So that takes care of boundary 1. Boundary 2, same idea. E and H are continuous. So for E, we have E sub I2 plus E sub R2 is equal to E sub T2. And H, again, we have these cosine factors, so square root of epsilon naught over mu naught, E sub I2 minus E sub R2, N1 cosine theta I2, square root of epsilon naught over mu naught, E sub T2, N sub S, the substrate, cosine theta T2. Okay, so boundary conditions. Now we go on here, and K N1 d cosine theta I2. Let's set that equal to K naught H. So K naught N1 d cosine theta I2 is K naught H. And just to simplify it a little bit, then we could say that E sub I2 is E sub T1 e to the I K naught H. So we're just propagating from here to here. And likewise, if we like, we can write that E sub R2 is E prime R2 e to the minus I K naught H. Yeah, this is, I did it mathematically, so instead of writing little e, I made capital E. So, and instead of making little I made capital I. So it's exponential. Now, depending on the book you look in, you may get some opposite signs. And the reason is I'm writing e to the I kz minus omega t, and some books will write e to the minus I kz minus omega t. So the end result will turn out to be the same, but in the middle here we'll get some different signs. So we simply take this here and we plug that back into the boundary conditions for surface 2. And so we get E2 is E sub T1, e to the I K naught H, plus E prime R2, e to the minus I K naught H. And then we get a similar expression for H that I won't bother to read. So now the interested student will solve these last two equations for E sub T1 and E prime R2. And he'll go back and plug it into the first two equations for boundary 1. And you're going to get that E1 is E2 cosine K naught H minus H2 I, so that's square root of minus 1, sine K naught H divided by gamma 1, where gamma 1 is square root of epsilon naught over mu naught, N1 cosine theta I2. Okay. And for H, you get H1 is, well, minus E2 gamma 1 I sine K naught H plus H2 cosine K naught H. So this is relating the E's and the H boundaries 1 to what we have for boundary 2. Now for the example we're working through, we had that E was perpendicular to the plane of the paper. If we went through the same derivation, but we made E in the plane of incidence, or in the plane of the paper, I should say, we would obtain a similar equation, except that gamma 1 is, instead of cosine up here, we have cosine down there. Okay. Well, we can rewrite this in matrix notation. Maybe if we could just zoom in just a little bit here. Okay, whoa, that's good. So in matrix notation, just E1, H1, E2, H2, and we have these factors here. K naught H minus I sine K naught H divided by gamma 1 minus gamma 1I sine K naught H and cosine K naught H. And so we can call this mess right here M1, and we'll give that the name of the characteristic matrix. So that's the characteristic matrix that relates the field at two adjacent boundaries here. And so it's going to turn out, if we have, say, more films, I could go from surface 2 to surface 3 with another M here. Or if I have many layers of films, I can just define an M for each layer, and I can multiply all these M's out, and so I could relate the incident E and H to what's leaving here by all these 2 by 2 matrices, where as long as I know what each layer is, I can calculate the M's for that particular layer. Okay? So maybe at this point you say, so what? I guess, I don't know. Are you thinking that? Too polite to say it? Okay. Well, so what? Well, what we're going to do now is we're going to see how to go from these M's to the expression for the amplitude coefficient of reflection and transmission. And so what we will do here is first we'll make a little definition here that gamma naught is square root of epsilon naught over mu naught n naught cosine theta I1. Gamma sub s, same thing, but n sub s and theta T2. And then we go back and we combine equations 1 and 4 and 10. 1 through 4 and 10, I should say. So that was the boundary conditions, and just a little matrix here. And we end up, and the interested student will go through all the details, I'm sure. We have lots of interested students here, you can see. So we will end up with this expression right here, which simply says that E sub I1 plus E sub R1 is M11 ET2 M12 ET2 gamma sub S. And E sub I1 minus E sub R1 gamma naught is M21 E2 ET2 plus M22 ET2 gamma S. Okay? And this will become a little more interesting if we plug in here, the amplitude reflectance is E sub R1 over E sub I1. I mean, that makes sense. E sub I1 is what's incident. E sub R1 is what's reflected up here. And the transmission here is E sub T2 over E sub I1. So it's simply E sub T2, what gets through here, divided by what was incident up here. And we take these and plug that back into here, and it drops right out very fast. That 1 plus R is M11T plus M12 gamma ST. 1 minus R gamma naught is M21T plus M22 gamma ST. And we could then solve this for R and T, and it's pretty straightforward, but being lazy, I did it in Mathematica, but it doesn't take much to do. And we get the result here. Hate to read this, but R is equal to this thing right here, and I will read it once, minus M21 plus M11 gamma naught minus M22 gamma S plus M12 gamma naught gamma S. Down in the basement, M21 plus M11 gamma naught plus M22 gamma S plus M12 gamma naught gamma S. And we have a similar expression here for T. Two gamma naught, and then same expression in the basement that we had for R. So the thing is that if we know, if we have a film, we know N and K for the film, we know angles of incidence, we can now calculate this matrix for this film, plug the elements of the matrix in here, and calculate either the reflection or the transmission. And then we could square these, or absolute value squared, and calculate the intensity reflection and intensity transmission. So maybe all this garbage we went through here works out pretty well after all. And, you know, all we have to do is calculate a 2 by 2 matrix for each layer. And if we have many layers, we could multiply all these matrices out and end up with a reflectance and transmittance. And for that, you get paid a lot of money, I'm told. Okay? Maybe there's more to it. I think the theory for thin films is pretty straightforward, but to actually make the thin films, it's a little black magic there, I think, that comes into play. Stuff that's not covered in a lot of courses, maybe. But that's where you make the money. Okay, well, let's go on here. We have 7 minutes and 28 seconds left. And talk about some films here. And the first is an AR coating, an anti-reflection coating. And just to make life simple, we will say we're at normal incidence. And that's often the case. But I mean, this is so general, you can, and especially you have it on the computer, you can put in any angle you want, and it works right out nicely. But we'll say we're normal incidence. And so gamma naught is square root of epsilon naught over mu naught n naught. Gamma sub s is the same except n sub s, and gamma 1 is the same except n1. And our elements here, the matrix, just become cosine minus I sine divided by gamma 1 minus gamma 1 I sine of k naught h, and the cosine here. And we have only one layer present, and so we will say the reflectivity here is R1. So all we have to do then is to come back here and plug in the parameters in here to R1, and we'll square that, and we'll get what the reflectance is. And so you can do that. So I just say R1 and plugged in what M11 was, and M12, and M21, and M22. And we get this mess, which I won't bother to read. And then plugged in what the gamma naughts were, and the gamma sub s, and the gamma 1. And we get this mess right here. And we keep working. We square that. And we get an even bigger mess here. Okay? Cosine squared, and something with the ends, and a sine squared, and something with the ends, and somewhat similar downstairs, except the minus signs become a plus sign. Horrible mess, but this is what your reflection is. Being lazy people, what we'll do, we'll look at this and we'll say, how can we make this simple? What can we possibly do? Well, one thing we could do is that we could make h times k naught to be pi over 2. And if we do that, the cosines will go away, and the sines become 1, and we'll get a simple equation. And, well, before I do that, if K naught H is pi over 2, K naught H for normal instances is 2 pi over lambda naught, lambda in vacuum, times ND. And so that says that ND is lambda naught over 4. So the optical thickness of this film is a quarter wave. Okay? So anyway, we plug in that we have a quarter wave film, so K naught H is pi over 2. And we get here, plugging in K naught H is pi over 2, we get a nice little expression that the reflectivity for a single layer film goes as minus N1 squared. I should go back here and say I should have had a subscript here. This should be N1 right there. I want to make sure that's... Anyway, we get the result here. The reflectivity goes as minus N1 squared plus N naught S, quantity squared, divided by N1 squared plus N naught NS squared. And if we want an AR coating, so no reflectivity, we solve this for 0, set that equal to 0, and we find that N1, the refractive index of the film, is equal to the square root of the index outside one side of the film times the index outside the other side of the film. So square root of N naught N sub S. And if N naught is 1, and let's say the film is the substrate is a piece of glass with index 1.5, the index of the film should be the square root of 1.5, or about 1.225. And if that is true, single layer, quarter wavelength, optical thickness, we get 0 reflectivity. Now, isn't that kind of neat? That's that normal incidence, right? But it's not going to vary real fast as you change angle. Cosine theta doesn't change too fast at the beginning as you go away from theta is equal to 0 degrees. So that would, that gives you 0 reflectivity. Well, the problem is finding a material that has an index of 1.225. And what they often use is mag fluoride, which has an index of 1.38, which is a little larger than we want. However, if it turns out that if we use a single quarter wave layer of this, it will reduce the reflectance from 4% to about 1% over the entire visible spectrum. Okay, so any questions on that? Well, I always thought that was a very neat result, and I can remember the first day sitting in class when I saw that result. It's great. Okay. Well, we can do better if we had more time by using more layers. And so what we're going to do next class is we're going to first do a 2-layer coating, index N2 on top of the substrate, and an index N1 on top of N2. And we'll go through and calculate the reflectance for that. And then we'll also look at using more layers and see what we can do to get both high reflectivity in some cases instead of low. So anyway, have a good weekend, and watch a lot of basketball, and do your homework. Maybe you should do your homework first and then watch basketball. And I'll see you bright and early next Tuesday morning.